Hello everybody, this is Yuanqing Wang. I'm a graduate student in John Codera Lab at Memorial Sloan Kettering Cancer Center. So in this paper with Josh and John, we asked the question whether it would be possible to construct a molecular mechanics force field in an end-to-end differentiable way. So first of all, what is molecular mechanics, or MM? MM is a class of physical model that abstract the atoms in your molecular or biomolecular system as spheres with charge and with mass connected by springs. So it has roots in Newton mechanics. Its popularity is largely because of its simplicity and its speed. So apart from the fact that the runtime complexity scales linearly with regard to the size of the system, it has also been optimized and parallelized on modern hardware. However, when you want to optimize the parameter set for a MM model, which is what we call a force field, it gets a little bit trickier. So how does force field parameterization works? So first, you have a molecular graph, and you have a scheme called atom typing scheme, where you assign different types to the atoms, which we call atom types. And you combine and compose the atom types to come up with bond angle torsion and non-bonded types. And from there, you have a tabulated set of parameters were attached to each of this atom bond angle torsion and non-bonded types to come up with a parameterized system, which can take coordinates to come up with energy. So let's just take a look at the first step. So this is a example of the assignment of atom types. Let's just take a look at the very first entry here. So this basically says that, okay, if you have a atom in your molecule or in your biomolecule, if it is a carbon, if it is an sp2 carbon, if it is bonded to either oxygen or sulfur using a double bond, then we say that this is a atom type C or atom type number 1. Okay, so as you can imagine, whenever you want to optimize the parameters you have in this force field, you can't optimize this last layer. You can't optimize this grouping of atoms. So the optimization is only possible up to the resolution of the atom typing schemes. And a new atom typing scheme would require human engineers to work on this for the very long time. So this has been published in 2004, and this GAF force field, which is generalized amber force field, has still been regarded as the gold standard in small molecule force field. However, with a closer look, we will realize that there are only 3 things that a atom typing scheme takes into consideration. It's the node attribute, so the element of the atom, be it a carbon, a nitrogen, and so forth, and the number of neighbors, so whether you have 2 neighbor or there are 4 neighbor or 3 neighbor, and lastly the attribute of the neighbor. So this would remind us of a very classic graph algorithm called a Weisfeld-Lehmann test, which is basically a tree expansion coloring scheme. And there have been papers comparing the expressiveness or the expressive power between graph neural networks and Weisfeld-Lehmann test. And it has been established that the graph neural network could be as powerful as Weisfeld-Lehmann test. So if we hypothesize that WL test can be as powerful as atom typing, then we can subsequently hypothesize that graph neural networks can also approximate atom typing. Okay, so first we experimentally validate this. So we put the legacy force field assigned types as the target for our classification, and we use a small graph neural network to fit this, and we get a relatively high accuracy. So if this is established, then we can move one step further and ask, okay, can we use a graph neural network to come up not typings of atoms, but embeddings of atoms, so it's continuous, and so that we can push this embeddings, we can combine them and pull them to come up with bond, angle, and torsion embeddings and push them through another layer of feed-forward layer to directly get atom, bond, angle, and torsion parameters. And with coordinates, we'll get energy. So imagine you have a data set, which we do have, and which are there are a few options out there. So if you have a data set with quantum mechanics derived energies with its coordinates and its corresponding chemical graphs, then you can imagine optimize our typing scheme or rather our parameterization scheme in an end-to-end differentiable manner. So this is what we did. So the top part is just a proof of concept where we fit to a system, and the second part is a fitting experiment to a QM system. So as is shown here, we achieved a slightly better performance compared to one of the state-of-the-art traditional molecular mechanics force field, which is called Parsley. So if you use our system, then the optimization of the parameterization process is possible from not only just the parameters you put on all of the atom bonds, angles, and torsions, but also the process to realize or to quantify the atom, the chemical environment of the atoms. If you are interested in our work, please see our poster as well as our preprint. Thank you.